Okay, here is our second lesson of Chapter 1. Focus today is graphing. Lots of graphing. Sketching a few functions, identifying some symmetry, a couple of things with applications, but that really just the basics of how to take a function that's in the form of an equation and to get it on a graph. It's kind of the name of the game for today. All right, where I want to start the discussion is on solution points. Okay, I've got a linear equation up at the top here, 10x minus 7, and I've got 2 points. And I just want to quickly check to see if those points are solutions. This is something I know you've done before, but it's just a good place to start the conversation here. What I would do is, I'm going to check 213 first, is plug in 13 for y, 2 for x, and really it's a matter of simplifying both sides to see if they reduce to the same thing. Keeping in mind the left side is already as simplified as it's going to get, it's just 13. So now the question becomes, does the right side simplify to 13? 10 times 2 is 20, minus 7. Okay. 213 is a solution. If I were to plot that point on a graph, it would be one of the points that would form the line 10x minus 7. Same thing with negative 3. I would do 10 times negative 1 minus 7. This is a different story as it simplifies to negative 3 equals negative 17. That equal sign needs a big slash through it because those two sides are not the same, and that point is not a solution point. Got another line down here, okay, because what we did up above is just look at a couple solution points. But if you want to get a sketch of a graph, typically what you do is just put together a collection of a handful of them. Sometimes the x values that you choose are really, really important. Other times they're really not. This one, based on the axes that I have, you're probably looking at picking points that are somewhere around x equals 0. If you wanted to at this point, you could certainly pause and you could fill out your table of solutions yourself. You get negative 10, negative 7 when you plug in 0. Put in 1, you get negative 4. Plug in 2, you get negative 1. 2 and 5. And typically what you're looking for, depending on what type of graph, somewhere between 5 to 7 points. That question comes up a lot if you're making your own table. 5 to 7, if you pick good points, like good x values to use, should give you a pretty good look as far as what the graph looks like. Because then, of course, putting together a graph is just a matter of plotting all those points. And my line approximately goes through all of those. Because given there is a lot more points that form that line, but I get a pretty good sense of what it looks like from those, what did I have? 6. Same idea down here. The only thing that's different in this problem is you have a function and it's not linear. It's a quadratic. Now, as the function type changes, given we have a lot more to talk about this chapter about different types of functions, right? I'm just starting with two that I'm thinking you're probably pretty familiar with, a line and a quadratic. That's typically a great place to start when you're looking at different types of functions. Quadratics have that parabola shape, and if I want to get a good look at it, it is pretty important that I get a special point called the vertex. That's the point where the graph changes direction. I want to make sure that particular point is included. It's another topic we'll get into with a lot of depth. For now, I know you've done it before, but for now, if I had to produce a sketch of a function where the x values are really important, I would probably give them to you for Chapter 1. Chapter 2 would be a different story. What I really want you to see here, though, is that it doesn't matter what type of function it is. You know, producing a sketch is the same, it follows the same procedure. You know, we need a table of solution points. I'm going to reflect that point and put it over on the other side. We need a table of solution points. 5 to 7. What does this one have? Again, 6. So far I seem to like 6 today. And then you need to plot those points. You know, and the shape of the graph really should take care of itself, and you should have a good look at it. Oh, we'll talk about symmetry here in a minute. Right now I want to talk about x and y intercepts. As you deal with functions that get a little bit more complicated, and notice on this one I've given you a cubic, a little more complicated than a quadratic. Producing graphs can get more complicated, and the x and y intercepts are often great reference points that we like to use, because no matter how complicated the equation is, there's a pretty similar procedure to go through to get these points. Now, y-intercepts you've done before, and we absolutely love to do the y-intercept. And you probably remember it by this. It's just not a hard point to get. Plug in 0 for x. Okay? So I'm looking for this y value where it crosses the y-axis, and I need to evaluate 0 cubed minus 4 times 0. And that comes out to be 0, which tells me right there at the origin, this graph goes through that point. X-intercepts, again, have a set procedure that I can follow to get them. It's just a little bit more complicated, because now I have to put in 0 for y, and I need to solve. Okay. With y-intercepts, I did not have to do that, and here I do. This can be a bit of work to do depending on how complicated the equation is. This one isn't terrible. I can take out a common factor of x in both terms, and I'm left with that. And then I have x squared minus 2, which is a quadratic now, after I took out that factor of x. Right? Remember, when you're solving, the point of factoring is then you can solve each factor by itself. And you would get solutions of x equals 0, which if you look at the y-intercept, I actually already knew that one. X equals negative 2, and x equals 2. That should give me a graph just like that. Now, you wouldn't necessarily know, or remember, I should say, that the tails go in those directions, and then it crosses at those x-intercepts and doesn't bounce back the other way. We'll get to that, right? Really what I want you to see from this slide is y-intercepts, plug in 0 for x. X-intercepts, you need to set equal to 0 and solve. Oh, now let's talk about symmetry. Okay, there's 3 different types that we'll look at. And here's what's going on. Let's say, and these points may not match exactly because I didn't make this graph super accurate. Let's say, like right here, that this graph goes through the point 4,2. Let's say this one does. And let's say this one does. Okay? And they all about do. I'm just kind of saying roughly. Okay? The first one doesn't really look like it does, but I just want to use the same point for all 3 of them. And don't think from this that every function always goes through the point 4,2. I mean, go back to our very first example when we check solution points. Some graphs do go through the point 4,2, some don't. I just want to use the same point. There's a pattern to symmetry over the x-axis, which down here, what you would see happen is we still are at the point 4, but now I have to go down, and I would also go through the point -2. Over here, over the y-axis, as I now head over to the other side, I have to go 4 units to the left, but it would still go through the y value of 2. And symmetry about the origin, I now have to go to the left, and I have to go down, but if it has that type of symmetry, it's going to be the same number of units. Okay? Now what I want to do for each one of these is put it in general terms. If x, y is a solution. Okay, now that line right there, that condition applies to all 3 of these. If I'm talking about symmetry over the x-axis, so is x negative y. Again, that's for symmetry over the x-axis. Okay? For any point that you have, that's a solution. If you just switch the y-coordinate, switch its sign, and you're still on that graph, you're talking about a scenario where you have symmetry over the x-axis. But remember, that has to be true for every single point on the graph. See if you could fill in the blank with these 2. Good point to pause, because it follows a pretty similar scenario, and I bet you can pick up on the pattern. If you're talking symmetry over the y-axis, so does negative xy. Okay? That would also be a solution. Again, every single point, you could just switch the coordinate of the x-axis, x-coordinate, and you still have another solution point. And as you may have predicted at this point, symmetry about the origin. Take every single solution point. If you switch the coordinates, or switch the sign of both coordinates, you still have a solution point. Okay? You may get a homework problem that would ask you to test to see if it has symmetry. You can't test every single point. Okay? The magic number we'll use is 3. If you see this pattern happen for 3 of the points, go ahead. And you couldn't have absolute certainty because it may have just been 3 weird points, but you'd be pretty certain it's got that type of symmetry. Here's the equation of a circle. Okay, again, it's one of those Chapter 1 learning targets where we're just kind of hopping around, right? Again, the theme today is all things graphs. All right, the equation of a circle looks like that. We need to know the point HK. That is the center on the circle that I have right here. That point is right there. That point is essential. We couldn't write a model for a circle unless we had that, because it tells us where the circle is. R is the radius, and that is, again, a number we must know. Okay, if we don't, we're just out of luck. You know, the center tells us where the circle is, the radius will tell us how big it is, and the radius is right here. Now if I go up to this equation with two pieces of information, one that the radius is 3, and -4, -2, those are the coordinates, excuse me, back it up here. -4, +2 is the center. We would be looking at this. X minus -4 squared plus y minus 2 squared equals 3 squared. If we went and plotted all the points that are formed by this equation, you would get that circle. Now I would clean it up a little bit here and say x plus 4 squared plus y minus 2, and I guess it wouldn't matter either way. You could just leave it as 3 squared, or you could say it's equal to 9. Now if you were given the equation, you need to be careful about that, because it's tempting to say that, you know, as it's written down on the bottom line, to say that the radius is 9. Remember, it's r squared. This represents an equation that has a radius of 3. All right, now this was a problem right here, and you'll see this come up on the notes that I do in these videos. This was a problem that we did in what I like to call our breakout sessions in class, where we split up into either partners or small groups, and we did this problem independently. I want you to do that too, even if you miss class. I want to give you one to do on your own. However, in these lessons, I do like to give you some instructions as to kind of where to go with these. All right, here's what we have. We have a quadratic model right here. This quadratic model is for men of medium frame from ages 25 to 59, and the x value is in inches, 62 to 76, which is 5'2" to 6'4". So what this model is going to do is we put in a height, and it gives us a recommended healthy body weight, kind of an average. Okay, the problem kind of implies that this number could vary, but it's going to give you like a ballpark. You know, the individual may weigh a little more and still be healthy, or a little less. This is kind of right in the middle. So what we're going to do here is, in this first part, you would put together a table of values, x and y. Okay, and in fact, it's very kind and tells you the x values to use. Okay, you would plug these into your quadratic, get that table, and then down here, you're going to plot them. Okay, be careful about your scale. All right, for the x values, I would use 62 to 76. Right, follow the table, and then after you make it, you're going to have a bunch of y values. That's going to tell you where y needs to start and where it needs to end. Okay, so get your axes on there and then plot them. Okay? What we're going to do down here, tends to be the point where you maybe need some clarification. We're then going to get interested in this male who is 71 inches tall. We want to give him a recommended healthy body weight. Okay, now notice we skipped over that on the table. Now there's two different ways we can do this after we have our graph. We could line it up and go to x equals 71, go up to the graph, and then go over to the y-axis, you know, because your graph is going to end up looking something right, and then you connect the points. It ends up kind of looking something like that. So you could go to 71, whoops, Should be a little neater with that. You could go up and then over, right, to get the recommendation for his weight. Okay? The other way you could do it is you could take 71 and you could just plug it in. Okay? You're going to do both. You know, as you're doing the graphical part, you're just getting an estimate, right? Now you might think, well, if you really want to know his recommended weight, why don't you just plug in 71, right? And if you just want like the actual answer to his recommended weight, that's probably a better way to do it. But what you're really after in these last two parts is we just want to see how good your graph was, right? That's why we want both numbers. The actual recommendation is going to be what we get when you plug 71 in for x, okay? What I want you to check is after you do that, and you have the estimate from your graph and the actual number, how close are they, okay? And I'll give you this last little tip before you go off and do this one. And I have an answer key in class, so if you want to see that, and you have questions about this one, come back and see that. What I'm expecting here is you should have an estimate from your graph within one at most 2 pounds. But realistically, probably within a pound is you should have an estimate of what the actual weight is.